Okay, for example 1, we just want to talk about what is an absolute max or absolute minimum. Sometimes they call them global max or global min, but that's the exact same thing. So on our first example, you can see it's a negative x squared. It's been moved up 3, so it's an upside down parabola. In this case, we have an absolute maximum when x is 0. An absolute maximum would have to be the biggest y value on the entire graph. You'll notice that this graph does not have an absolute minimum, and that's because the graph goes down forever on both sides. So there is no lowest point, but there is a highest point. That highest point would be 3. So we would say that the absolute maximum is equal to 3, and it happens when x is 0. On the other side, you'll notice that we have an absolute minimum. The absolute minimum is equal to -1, and it happens when x is equal to 0. But this graph over here does not have an absolute maximum because there is no highest point on the graph. Okay, for example number 2, we're going to look at a local max or min. Sometimes they call it relative max or min. They are the same thing. Now, for a local maximum, all you have to be is the largest y value in any neighborhood containing that point. So it can't be an endpoint, but as long as you're inside of any interval that contains that point, and you are the highest value, the biggest y value, then we would say that you would have a local maximum at that spot. In order to be a local minimum, you just have to be the lowest value inside any interval that contains that point, and then we would say that that is a local minimum. Now, if we go back to the first example, I want to point out that this is also a local maximum, and this is also a local minimum, because there is some neighborhood that I can draw where those spots are the highest value in this situation and the lowest value in this situation. So the left one is also a local maximum, and the right one is also a local minimum. I also want to point out that the x value is just where it happens. So for a max, the x value is where it happens, but the maximum is actually the y value. For the minimum, the x value is, again, just where it happens, but the actual minimum value is going to be the y value. Okay, now we're doing example number 3. Okay, this example is meant to point out that when the derivative is 0, another way of saying that is that the slope is 0. And you can see that when you have a slope of 0, that's one place where you could get a max or min. So what we're going to do is we're going to take our function and we're going to do the derivative. Then we're going to set it equal to 0. And then we'll solve it for x. Now, x equals 0 is one of the places where our slope is 0. So it's possible that we could get a max or min at that spot. In this case, we do have a minimum value. This minimum can be considered a local minimum, but it could also be considered an absolute minimum. In calculus, there's another way we can find a max or minimum, and that would be if the derivative was undefined. That's the same thing as saying that the slope is undefined. And we're saying even if there's an endpoint, remember the derivative at an endpoint is undefined. Now I do want to clarify about at an endpoint. You cannot have a relative maximum at an endpoint, but you can have an absolute maximum. In order to get a relative maximum, you must be inside of an interval that contains that point. Same thing for relative minimum. You must be inside of an interval that contains that point. So an endpoint doesn't work for a local max or min. But if your derivative is undefined, like this situation here, that is one more place where you might have a max or a min. Now, how would we do the derivative for the absolute value of x? Well, we would want to get rid of the absolute value. So I'm going to write a piecewise function to describe the absolute value of x. So I'm saying when x is greater than or equal to 0, it's just y equals x. And when x is less than 0, it's y equals negative x. Of course, the equal sign could go on either one of those. It doesn't matter. Now we'll have a piecewise derivative. You can see that when x is greater than 0, the slope is just positive 1. When x is strictly less than 0, the slope here is negative 1. Now what is the derivative when x is equal to 0? Well, that's going to be undefined because the derivative is just a limit. And you can see the limit from the right is +1, the limit from the left is -1. That's not the same number, so that limit does not exist. So in this case, the derivative at x equals 0 does not exist. So the derivative would be undefined. So that means that at that spot, there could be a max or min. Okay, now we're doing example number 5 out of 6. The directions would be to find the max or min. We know that there are two places where you can find a max or min. One of them is when your derivative is 0, and the other one is when your derivative is undefined. So let's do the derivative. Now, because this is just a polynomial, there is nowhere that the derivative would be undefined. But there is a spot where the derivative might equal 0. So we're going to take that derivative and we're going to set it equal to 0. And then we'll solve. Let's divide both sides by 3. Then we'll factor it. Okay, we get x is equal to -5 and x is equal to +3. Now we're going to call these numbers critical numbers. A critical number is where your derivative is 0 or where your derivative is undefined. What we're going to want to do with those critical numbers is we're going to want to put them on our number line, and then we're going to want to check the value of the derivative on both sides. Okay, let's check the left side of -5. I could plug in a number like -6 and see what I get. You plug in the -6 and you simplify it, you get a +27. Now the fact that your derivative is positive at that spot, it means that your function is going to be increasing on that interval. You can see that if you look at the graph, our function is increasing all the way until x equals -5. Now let's check the right side of -5. We can plug in something like 0. When I plug in 0, I get -45. What's important is that it's negative. So I'm saying my first derivative is negative when I plug in 0. And so that means my original function is going to be decreasing on that entire interval from -5 to 3. If you look at the graph, you can see we are decreasing from -5 all the way to 3. Okay, the last thing I want to check is when x is greater than 3, is the derivative positive or negative? So I'm going to plug in an x value of 4. Then I get +27. Since my derivative is positive, it means my original function is going to be increasing on that interval. If you look at the graph, you can see when x is greater than 3, our function is increasing. Now, if you look at our chart, the bottom row is all the x values. You can see we have our two critical numbers, and we tested in between those critical numbers. We plugged in any x value between those numbers. The second row is the value of the derivative at those spots. So the derivative is going to be positive when x is less than -5. And so that means our original function is going to be increasing when x is less than -5. Then I plugged in any x value inside here. I found out my derivative was negative, and that meant my original function would be decreasing on that interval. Then I plugged in any x value bigger than 3. I plugged it into my derivative and found out that my derivative was positive on that interval. So my original function would be increasing on that interval. Now what my chart is telling me is that my original function is going to be increasing, then decreasing, and then increasing again. So I would expect to have a maximum value when x is equal to -5, and I would expect a minimum value when x is 3. If you look at the real graph, you can see that it's just a local minimum at x equals 3 and a local max at x equals -5. And that's because the graph goes up forever, and it also goes down forever on the other side. So there is no absolute max or absolute min, just a local max and just a local minimum. Okay, after filling out this chart, we found out that when x is equal to -5, we have a relative maximum value. If we want to know what the relative maximum is, we would have to plug a -5 into this function. Now, when you plug in a -5 into the function, you get 158. So that means the relative max is equal to 158. The x equals -5 is just where the max occurs, but the max is the number 158. It's the y value. We could do the same thing for x is equal to 3. If we plug in x is equal to 3, we get -98. So -98 is the actual minimum value. We call it a relative minimum, and that's because there is no absolute minimum. But x is equal to 3 is just where the minimum occurs. The actual minimum is the number -98. Okay, this is our last example, number 6 out of 6. we're going to look at x to the 2/3. If you remember what x to the 1/3 looks like, x to the 1/3 looks something like this. But to get x to the 2/3, we have to square it. And that would make this piece down here reflect up. And so that's why you're getting this piece up here on the top left. So that's the function x to the 2/3. You can see the slope over here is positive, and the slope over here is negative. So at this spot, the slope is going to be undefined. Okay, again, we're going to be looking for the absolute max or the absolute min. In order to do that, we need to find where our derivative is either 0 or undefined. So if we do the derivative, the 2/3 comes down, and the new power is 1 less. We can rewrite that. We get 2/3, and then the third root x. Again, we're looking for critical numbers. That's where our derivative is either 0 or undefined. We have a fraction, and the fraction is only going to be 0 if the top is 0. So we need 2 to equal 0. That's never going to happen. And our derivative would be undefined whenever the bottom is 0. So you can set that equal to 0 and solve it. You'll get x equals 0. So x equals 0 is going to be one of our critical numbers that we're going to take a look at. I'm going to fill out our chart. Okay, I need to choose a number that's less than 0. So I can choose -1. And if I plug it into my derivative, I would get 2 divided by 3 times the third root of -1. Now the third root of -1 is just going to be -1. So I get -2/3, but what's important is that it's negative. So the derivative is negative when x is -1. Now let's plug in a number over here, like +1. Okay, when I plug in +1, I get +2/3, which is positive. Since my derivative was positive, that means my original function is going to be increasing on that interval. And over here where my derivative was negative, my original function is going to be decreasing on that interval. So usually when we do these, we don't have the picture of the graph. So the chart is telling me that my graph is decreasing and then increasing. So I'm expecting to have a minimum when x is 0. Now to find out what the minimum is when x is 0, you're going to want to plug in x equals 0 into your original function. If you do that, you're going to get 0 for the y value. So we're getting 0 for the x value and 0 for the y value. Now this is considered an absolute minimum because it's the lowest value on the graph. And it's also considered a relative minimum because it is inside of an interval that contains that point. And it's the lowest value in that interval. Okay, after doing this example, we can say that when x is equal to 0, we have a relative minimum value of y equals 0. Now we would have to be a little bit more careful in this situation if our function was not continuous. And we'll talk about those examples later when we get them. But just to review what we're doing here, we're looking for our critical number, and that's where your first derivative is either 0 or undefined. Then we're plugging in numbers into our derivative. We're going to choose numbers just to the left of 0, could be -1. Plug it into your derivative and see if you get positive or negative. When you get a negative for your derivative, it means your original function is decreasing. Then over here, we might plug in a +1, anything to the right of 0. Plug it into your derivative. If you get positive, it means your original function is increasing. So we usually don't have the picture of the graph. But based on this chart, we know our function is decreasing until x equals 0, and then increasing afterwards. So there's probably going to be a minimum at x equals 0.